SwayamPrabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. Today I am going to talk to you about electrolytic in process dressing and grinding, a technique to nano surface finish. Acknowledgement. Lecture delivered by Professor K. Patham from PSG College of Technology, Coimbatore at IIT Kanpur in a short-term training program. Then again Professor Fatima, who the electrolytic in-process dressing grinding, she wrote a chapter in the book on Introduction to Micromachining, which was edited by Dr. V.K. Jain, published by Narosa Publishing House. Outline of the presentation. First, I am going to talk about ELID and introduction, then nano surface finish by grinding, present and future developments, conclusions. Introduction and mechanism of working of electrolytic in process dressing grinding. Electrolytic in process dressing grinding, that is ELID, it is abbreviated as ELID. ELID stands for electrolytic in process dressing and grinding. It is one of the methods that realizes mirror surface finish on hard and brittle materials, because we all know it is very difficult to obtain very fine surface finish on the hard and brittle materials. Components of the system, ELID system: metal bonded diamond grinding wheel, an electrode, a power supply and electrolyte. You can see here, this is the electrode, this is the electrolyte supply, this is the grinding wheel, and here is the workpiece, and this is the power supply. Continuous dressing of wheel while the part is being machined finished. This is an important feature of this process, that you are continuously dressing the grinding wheel when finishing is taking place, so that you need not to stop the process and do the dressing of the grinding wheel. It minimizes the problem of wheel loading and glazing, because you are continuously dressing it during the process itself and making uninterrupted grinding. This is the unique feature of this process, because in general grinding you stop the grinding process, then you do the dressing of the grinding wheel, then you restart it. Here it is not required during the process itself. You can dress the grinding wheel and you can continue the grinding process. The electrolytic in process dressing grinding uses hard metal bonded grinding wheel. This is hard metal bonded grinding wheel. This simply means that the grinding wheel is electrically conductive, and if it is electrically conductive, electrolysis can be performed, and we will see how it is getting automatically dressed during the grinding process. So, hard metal bonded grinding wheel of very fine abrasive grades to perform deterministic material remover. The ELID is a hybrid process which consists of an electrolytic process for dressing of grinding wheel and a mechanical grinding process for material removal from the workpiece, that you can see over here. Electrode is there and electrolyte is used for that purpose. Mechanism of ELID. Now, this is very important slide to understand the mechanism of ELID grinding, dressing. Now, this is the metal bonded grinding wheel. Now, this is the metal bond and these are the abrasive particles which are electrically non-conductive. Now, when electrolyte is being supplied over this, then oxide layer is formed due to the electrochemical reaction, as you can see here, and definitely this oxide layer is weaker than the parent metal bond, and these are the sharp grits and they are going to perform the dressing or grinding process. Now, you can see here in the second slide, wherever the this becomes oxide layer becomes weak and there is the large force on the abrasive particles, they detach from the bonding material and separate out. So, you can see here the crack is being formed over here, dislodged grit over here, and these are the dull grits. These are the sharp grits, as you can see over here, but this is the dull grit, these are the dull grits, and once they become dull, the force that is acting becomes larger compared to the one which is acting over here. As a result of that, these abrasive particles, they dislodge, as you can see over here, and further you can see breakage of the layer is there, dislodging of the abrasive particles is there, and this becomes the thinner oxide layer, and once it is thinner, further processing takes place, as we will see here. As the grinding process progresses, diamond grits wear out, that is what I have told you here, and the normal force exerted on the grit produces cracks on the bonding matrix, that is over here. The breakage of insulating layer occurs by the accumulation of the normal forces exerted on the grits. And this is the insulating layer which has been formed, oxide layer, and the bond grits dislodge with broken layer. These are the bond grits and these are the broken layer, both of them are dislodging or separating out from the grinding wheel. Consequently, the thickness of the oxide layer becomes thin. So, you can see here this is thinner compared to the oxide layer over here, and electrical conductivity of the wheel surface increases because this non-conducting layer has been, part of the non-conducting layer has been removed. So, as a result, the electrolytic dressing restarts with the flow out of bonding material from the grinding wheel. Once this flow out or removal of the bonding material starts, then these borne out grits are removed and fresh abrasive particles, they are protruding outside, and the oxide layer formation further takes place, and as you can see this oxide layer has increased, but the sharp abrasive particles are protruding. So, therefore, the protrusion of diamond grits remains constant during ELID grinding. So, this protrusion remains more or less constant during ELID grinding process. So, this is how this ELID process performs the grinding and dressing during the same period. ELID setup and ELID mechanism, part of this mechanism I have already explained to you. This is the setup, which is the workpiece is there, electrolyte supply is there, and then carbon brush is there, and fine adjustment for electrode can be done. Electrode is here, that we have seen in the earlier slide also. This part of this I have already explained to you, that this is the borne out grit, thin layer, etc. are there, and this I need not to go through once again. Now, this you can see over here schematic diagram of ELID, which was proposed by Murata. You can see here over this is the workpiece on which the forces are acting. This is the electrolyte supply, that is electroconductive coolant is coming over here, and this is connected to the electric current negative, and here you can see this is the positive, this is connected to the positive, that is the anode, and this is the cathode, and this is the grinding wheel because it is having the bonding material. So, this becomes a workpiece, and from the workpiece material is being removed, as we all know, during the electrochemical machining process. So, once this electrolysis takes place, material gets or material forms the oxide layer like this over here, and due to the mechanical forces this gets separated out, as we have seen in the earlier slide also, and then again once it gets separated out, fresh abrasive particles they protrude and grinding again restarts. This is the another photographic view of the same. This is the conductive workpiece, this is the copper and another things are there, diamond particles are there. Now, there are the various types of the ELID processes. This is the one I have explained to you. This is the another one you can see here. A power source is here and brushes are there, and you can see coolant is being supplied over here, and you can see here conductive workpiece is there, and copper as the bonding material is there, abrasive particles are there, diamond abrasive particles, these are diamond abrasive particles, and steel wheel substrate is there. Now, there is another type where you can see here, this is the workpiece, this is the insulator, coolant you are supplying over here, x, y, z directions are there, pulse power supply can be given over here, alternating pulse generator is there. From DC power you are creating alternating pulses for the current, and you can see here phenomena remains the same as I have already explained to you, only slight changes are there in this setup and the earlier setup. This is the wheel, this is the workpiece, you can see here abrasive particles are protruding here which are not visible, and same phenomena is taking place. This is the ELID 3 setup. Working mechanism, you can see here the ELID grinding system consists of conductive metal bonded grinding wheel, we have already seen it, and electrolyte which covers 1/6 to 1/4 of the periphery of the wheel. That electrode was there which is covering 1/6 or 1/4 of the periphery. I hope you remember this is used. This electrode, what it is doing is, it is removing the material, or it is making the electrolytic reaction to take place, so that the oxide layer is formed, and then that oxide layer is slowly removed and fresh abrasive particles protrude over there. A DC pulse power supply is there which can be converted into pulsed power, this AC also in some cases, and an electrolyte is there. A grinding wheel acts as an anode, and which we normally call as workpiece in case of electrochemical machining, because material is being removed. Here also the material is being removed from the grinding wheel, so that the fresh diamond abrasive particles protrude, those which have borne out already, and once they are borne out because of the larger force, they are separated out from the grinding wheel, and the electrode acts as a cathode. A small gap of 0.1 to 0.3 millimeter, that is 100 to 300 micrometer, is maintained between the electrodes in order to enable the electrolyte to pass. So, electrode, this gap is maintained between the electrode, external electrode, and the anode. This electrode works as the cathode, and this grinding wheel works as the anode or the workpiece from where the material is being removed. During electrolysis, the metal ions flow out from the wheel surface and form oxide, and we have already seen this oxide film reddish in color which is being formed. The prolonged electrolysis leads to the oxidized layer deposition on the grinding wheel. The reaction during ELID can be described as follows. Metal, you get this ions and electrons, H2O is there, you get hydrogen ion and OH ion, and again this metal combines with this and it forms metal hydroxide. M is bond material of the wheel, that may be copper or some other material. So, cuprous hydroxide, cupric hydroxide, depending upon the conditions existing in the interelectrode gap, it will be decided whether cuprous is formed or cupric is formed. Deposition of the oxidized layer reduces conductivity of the wheel, because oxidized layer is partially conducting or non-conducting, and that is why the conductivity of the grinding wheel reduces. I am saying partially because in certain compositions this may be partially conducted, but in many cases or most of the cases it is electrically non-conducting. So, reduces conductivity of wheel and prevents the wheel from further oxidation, because electrolyte cannot directly react or contact with the bonding material, that is copper or some other material, because in between oxide layer is there. A certain amount of oxidized layer is scrubbed off during grinding due to the wheel work interaction. As a result, the electrolysis is automatically restarts, or electrolysis automatically restarts. This cycle repeatedly occurs throughout the grinding process, and this is how you can see this dressing of the grinding wheel is taking place during the grinding process itself. Electrical parameters in this particular process are current, voltage, pulse on time, pulse off time, and current duty ratio. And grinding parameters are feed rate, depth of cut, spindle rotational speed. All these parameters, they are going to govern the quality of the products being finished or machined. And so, before really using it for a new product, you should optimize the variable parameters like current, voltage, on time, off time, feed rate, depth of cut and rotational speed, because these are the parameters which are going to decide or control the performance of the ELID process. Two types of grinding wheels are used in ELID. Type 1, metal bonded diamond CBN, that is cubic boron nitride grinding wheels, and type 2, metal resin bonded diamond cubic boron nitride grinding wheels. So, both types are used depending upon the workpiece material and other compositions. Type 1 wheels, cast iron or copper is used as a bonding material. A small amount of cobalt is added with the bond material for better grinding performance. Type 2 wheel, metal, normally copper, and resin are mixed into a definite ratio for a better performance. Now, grades of the grinding wheels, 325 to 300,000. Average grid size is 38 micrometer to 5 nanometer. These are the very fine abrasive particles, these 5 nanometer abrasive particles. ELID types. Types of ELID, 4 classes are mentioned in the literature about the types of the ELID process. Let us try to understand briefly what they are. Principle of in-process dressing is similar for all the methods. This is very important. In-process dressing principle remains the same in all the cases. Types of ELID, ELID 1, electrolytic in-process dressing. Wheels are straight, cup or tapered, electrode material copper or graphite, arc shaped electrodes are there. Now, this is the 2 ELID 2. Now, you can see the difference over here. Anyway, let me just start. ELID 2 electrolytic interval dressing, finishing of internal surfaces of small or micro holes drilled on a hard and brittle material. This is the hard and brittle material, and this is the internal surface of the hole which is to be finished, and this is the grinding wheel, and this is the coolant which is there. And the ELID technique, ELID 1 technique, not suitable for micro hole machining, difficulty in mounting of electrodes, it uses small sintered metal bonded grinding wheels of small diameter. Now, you can see here, this is a truing tool, this is the grinding wheel, here is the pulse power supply resistance is there, you can see the electrode, and this is the grinding wheel, and externally they are not in contact, and it is electrode is there, electrolyte is being supplied over here, you can see clearly. So, between the electrode and the grinding wheel there is the gap, that is known as inter electrode gap, and electrolyte is being supplied. So, electrolysis will take place over here. Once the electrolysis takes place, oxide layer will be formed on the grinding wheel, and that oxide layer get scrubbed off slowly as the forces on the abrasive particles increase. So, you can see here electrolyte, electrode, wheel and power supply is there, and finally, it is able to finish the internal surfaces. So, important thing is there you are doing continuously, here you can do intermittently also. Here you are doing it intermittently, because here dressing, here grinding is taking place, that time you are not using this electrode. Once it is out, then you are using electrode and doing the dressing of the grinding wheel. The small grinding wheels can be pre-dressed using electrolysis in order to gain sufficient grain protrusion. We have already seen the grain protrusion. Once you do the electrolysis and you remove the oxide layer, then fresh grains, new grains, they start protruding outside the grinding wheel, and here you are doing outside dressing also. The grinding wheel is dressed at definite intervals based on the grinding force. So, based on the grinding force, how fast it is getting borne out, and once it is borne out and you do the dressing externally. So, you can clearly see the difference in ELID 1, where you are continuously dressing the grinding wheel. In ELID 2, you are intermittently dressing the grinding wheel, and at that point of time you are really not finishing the internal holes, but in one you are doing both the things simultaneously. You can see this is the grinding of steel using ELID 3, this is the third version, nozzle for electrolyte, metal resin bonded wheel is there, workpiece is there, and pulse power supply is there. In ELID 3, electrolytic electrode-less dressing, figure shows in the figure 4 in preceding slide shows the schematic illustration of ELID 3, we have seen it. Now, here embedding of swarf on the grinding wheel surface reduces the wheel effectiveness. For machining conductive materials, metal resin bonded grinding wheels are used. Here you are using metal resin bonded grinding wheels. Now, conductive workpiece acts as electrode, this is the conductive workpiece. Electrolysis occurs between grinding wheel and workpiece, this is the grinding wheel workpiece. Electrolysis will take place once it goes inside. Electrolytic layer formed on the workpiece is removed by diamond grits during the grinding process, that is having the diamond grits, and you are removing the oxide layer internally from this. That simply, to me, it indicates feed rate of work table grinding wheel should be appropriately decided to avoid sparking between electrodes, that is workpiece and grinding wheel. This is very important. Sparking should be avoided between this and this, if they are very close to each other, uncontrolled manner, then sparking will take place and it will damage both grinding wheel as well as workpiece. So, that should be avoided. So, you should be able to control the inter-electrode gap between the two. So, here you can see clearly that in one, which is used for all kind of the workpieces except very small, grinding and dressing both are taking place simultaneously. In type 2, grinding and dressing both are taking intermittently, not simultaneously. In 3, both are taking simultaneously, but it is for internal holes and of large sizes. ELID 3A, electrolytic electrodeless dressing using alternating current. In the earlier case, in all the 3 cases we have used electrode, so that the electrolysis takes place between the workpiece and the electrode. Here it says electrolytic electrodeless dressing using alternating current. AC produces a thick oxide film on the workpiece. AC means alternative current is being used. So, here DC power supply, it is converted into alternative pulse generator. Tool is negative, workpiece is positive, as you can see over here. This is a metal resin bonded grinding wheel which is finishing it, and you are supplying the alternating current. That simply means it is positive and negative alternatively. So, you can see here this is the wheel and it is the metal ions, they are coming out from the wheel because it is positive at this point of time and this workpiece becomes negative. So, material is being removed from the grinding wheel and dressing is taking place, and you can see here this is the oxide layer formed on the workpiece, and this oxide layer, that is blackish in color, is removed by the abrasive particles. They may be diamond or some other abrasive particles, and they are removing this oxide layer, so that continuity of the electrical, for the flow of the electrical current takes place between the wheel and the workpiece, and this, once this layer is removed, then continuously the electrolysis is taking place, and once this oxide layer slowly forms, then that stops, and then abrasive particles have to remove this. Wheel is negative, as you can see here, and workpiece is positive. So, you have seen 4 different types of the ELID, ELID 1, ELID 2, ELID 3 and 3A. It prevents direct current, it prevents direct contact between the grinding wheel and the workpiece. As you can see over here, there is no direct contact between the two. Electric discharge between the wheel and workpiece is completely eliminated, and the ground surface finish is improved. Mechanism of the ELID grinding. The geometrical accuracy of the workpiece is strongly influenced by the wear rate of the grinding wheels. The grinding ratio G ELID is an important and a useful measure in grinding. You can see here G ELID is given by volume of material oxidized on the wheel and volume of oxidized layer removed during the grinding process and volume of material removed from the workpiece. So, whatever is being removed from this grinding wheel divided by workpiece, that will give you the G ELID. Now, this is what you can see over here, wear mechanism of ELID of grinding wheel. We have seen it. This is the grinding zone is there, this is the oxidation zone is here. Here you have a point on the wheel, and this is the relationship that you can see at different locations A, B, C, B, A, D, C, B, A. So, here you can see these points are there. So, this is the maximum thickness of the oxidized layer. So, maximum thickness of the oxidized layer is on C and V. This is the C and this is the V, and at other locations it is reducing. Note, the maximum thickness is obtained only during pre-dressing. The oxidized layer deposited on the grinding wheel prevents further oxidation of bond material, because oxidized layer is non-conductive. The oxidized bond material is removed from the wheel surface due to mechanical wear, that is due to the forces being applied by the abrasive particles on the oxidized layer. Mechanism of the ELID grinding, Omori et al. They published a paper based on this. You can see over here, same thing, more or less the same thing, mechanism of the ELID grinding that we have seen. The new trued grinding wheel is electrolyte. This is the new grinding wheel, and you can see the protrusion of all abrasive particles is quite large. But here in the second phase, if you see, this is the oxidized layer being formed. So, the protrusion of the abrasive particle is continuously reducing, and if you go here, the oxidized layer is removed during grinding, because it becomes weak and the larger forces are acting on the abrasive particle. So, they separate out or they fracture and remove the oxide layer, and you have the worn out grit also, and chips are also there, and beginning of the grinding and wear of oxidized layer, end of grind, and this is the wear of the oxidized layer. So, the wear of the oxidized layer stimulate electrolysis. So, you can see this is interesting. You can see here metal bond is there, layer metal bond interface is there. This is the enlarged view of this interaction, and oxide layer is also being formed over here. You can see clearly that is being formed. So, this is how really it is working, and this is taken from the paper from NUS, National University of Singapore. It is SEM view of the dressed wheel. This wheel has been dressed, and this is the scanning electron microscope view of the dressed wheel, and this is how it is happening. You can see here, this is a water soluble grinding liquid, this is the electrode, this is the grinding wheel, and it is made as anode, that is positive, and this is the workpiece which is being ground, and this is the table feed being given to the workpiece. There is another report on electrolytic in process dressing. Second report, electrolytic dressing is not a new technique in manufacturing. However, the following reports are significant. Let us see these two reports which appeared in the journal. Murata et al. In 1985, Japan. Application abrasive cutoff, abrasive size coarse 100, number 100 for grinding, material used ceramics. Observations: free from wheel loading, surface finish is improved, low grinding forces, high wear resistance. Claim ELID is an efficient technique. This was the claim by Murata et al. In their paper. On the other hand, in 1990, again from Japan, Omori et al. They published their report, and they say this is used for finishing purposes. Murata used it for cutting off purposes. Here they have used super abrasives from 4000 number. This they were using it for micro grinding. They used it for various hard and brittle materials like free from wheel loading, mirror surface finish was obtained, and low and stable grinding forces were acting, and wear resistance was not reported, and easy implementation suitable for conventional machining. So, this is the same picture which we have already seen over here. This was published by Murata, and the ELID grinding setup consists of this I have explained to you: metal bonded wheel, electrode, electrolyte, and power supply, and mechanism also we have discussed. Now, ELID grinding setup used for the experiment, let us see it. Here is the power supply for the ELID. Here you have the ELID wheel, brush, electrode, and electrolyte. You can see this is the wheel, electrode, this is the brush, and this is the electrolyte, and then you have the LOH optical grinding machine is there, full grinding machine, optical grinding machine. This is where from you can control it, And this is the outer look of the machine, and this is the lens which can be finished, glass blanks which can be finished on this machine. Then parametric analysis of the ELID process, effect of current duty ratio. The current duty ratio RC is the ratio between T on and the cycle time as shown here. Current duty ratio T on over T on plus off. Now, this is interesting one from the paper of Professor Fatima. This is the current duty ratio and this is the surface roughness RA. Now, you can see here this surface roughness is continuously improving as the current duty ratio is improving and stabilizes beyond a certain value, that is around beyond 60, it is beyond 50 rather, it is trying to stabilize it. On the other hand, wheel wear ratio is continuously increasing as the current duty ratio is increasing, because as the duty ratio increases, T on is increasing, and as a result of that, it is that current pulse is acting for the longer time and the wheel ratio is increasing continuously. An increase in current duty ratio increases the wear rate of the grinding wheel, that we can see here, and then you have the wheel wear rate affects geometrical accuracy of the workpiece. This is very important, because if wheel wear is fast, then it will affect the geometrical accuracy and tolerances of the workpiece which is being finished. Wheel spindle speed is limited from 1500 RPM to 3500 RPM. The depth of cut, this is the limitation of the machine. The depth of cut is chosen based on the grit size of the grinding wheel used and the accuracy of the grinding machine, because how much is the protrusion of individual grits, that will decide what can be the depth of cut, and to some extent it depends upon the machine also. Wheels should be dressed with low RC value in order to achieve the shape accuracy. RC is given over here. ELID is not suitable for high speed grinding except the case of ELID 2, which we have already seen. So, the wheel spindle speed is limited to 1500 to 3500 RPM. Generally, the depth of cut has been chosen as half the grit size, because as I have mentioned already, it depends upon the protrusion of the grits on the grinding wheel also. Wrong selection and combination of ELID and grinding parameters certainly leads to unsatisfactory results and ambiguities on the finished component. As you can see here, average grit size can be calculated by this formula. Grinding and micro nano grinding, whether they are same or different, let us see it. Grinding and micro grinding, there are certain differences which are shown in this particular slide. In grinding, material removal process is there, high volume of material removal is there, any type of material can be ground, performed with coarse abrasives. Normally grinding as such is performed with this coarse means comparatively coarse abrasive. Wheel hardness can be soft grade or it can be medium grade. Self sharpening ability is there in the grinding process, but in micro grinding, precision finishing process, very low volume of material is being removed, say micrometer cube or nanometer cube. Especially very hard and brittle materials are ground performed with super fine abrasives. Here you are using coarse abrasive, here you are using super fine abrasive, that means abrasive size is very, very small. Hard metal or metal resin bonded wheels are used. In process dressing is necessary you can see here turning, material removal processes, turning, grinding, milling, drilling, we know already these processes. Now, here in this particular case, the you can see here the grinding is taking place. These are the micro nano shifts or deep over here. This is the one that you can see here, and here is the void, that is mean space between the two abrasive particles. While here you have the bonding material, this is the bonding material, these are the abrasive particles. So, bonding material is holding them, and these are the bond grits over there, and this is the chip being formed. Deterministic micro grinding is deterministic. Hard wheel bond materials are used. Hard and brittle materials can be finished. Wheel loading, in process dressing is taking place, as we have seen. In some cases it is offline dressing, and in some cases it is in process dressing in ELID 1, ELID 2, ELID 3 and ELID 3A. So, micro grinding is slightly different from the grinding process. Chance wire grinding, a practical example. Chance wire ELID grinding, ELID MRF process chain. MRF is magneto-rheological finishing. Here both are tried to combine both of them, so that you get the better results. Experiments on ELID as a pre-process for MRF are performed to analyze its usefulness. That simply means first you perform the ELID, you get a certain surface finish, and after performing the ELID process you go for the MRF, magneto-rheological finishing, which gives you better surface finish after grinding. Disadvantage of nano ground surfaces, you can find ground marks over there, surface integrity and subsurface damage. These are some of the problems that you find in case of micro grinding. In this experiment, commercial MRF machine that was built first time by QED Rochester, USA was used for performing the experiments. ELID MRF process plant, the magneto-rheological finishing is a precision finishing profile correction process widely used by the optical industry, because there you need very fine surface finish, maybe even less than 1 nanometer, and there you use this chain, ELID MRF chain, and you know this ELID MRF becomes a hybrid process. ELID itself is a hybrid process. By adding MRF process you further hybridize it, because you have 3 processes: grinding, electrolysis, electrochemical process and MRF process. The process needs a pre-process to finish the optical components with high stringent specifications. That you can see over here. This is a picture of QED machine. This is the V and this is the component to be finished. You can see here must be completely free from mid frequency error. This is the one, this is low frequency or 1 frequency. You can have less than below 1 micrometer. Mid frequency error must be completely free from mid frequency error that conducting MRF. High frequency error, surface roughness, mirror surface finish less than few nanometer. That is what I have mentioned to you, nanometer, few nanometers, and subsurface damages are there that may be below 1 micron. So, these are the requirements for MRF process. ELID MRF process chain is suitable for industries. You can see here the triangle shows the requirements of a successful process. Let us start from here. Requirements of suitability of a process: high precision suitable for the present and future optical industries, low processing time, high production, less rejection and low investment cost. Results of ELID grinding: analysis of ELID ground surface, a sphere surface, fine ground with 4000 number grits. You can see here surface finish RA, mid spatial frequency that you can see here. This is the graph given over here, and this is the subsurface damage dimple method that you can see here. So, fine surface finish free from mid frequency error, low subsurface damage that you can see over here, and it is suitable for MRF finishing. Means after obtaining the ELID surface of this nature, you can go for MRF, magnetorheological finishing process to perform. These are the results of ELID MRF process. It is free, error free, mirror surface finish is obtained, negligible subsurface damage is there, mid frequency error, low frequency or form error, high frequency error, surface roughness and subsurface damages. The final results from the ELID MRF process chain. Form accuracy depends on the machine accuracy, wear rate of the grinding wheel and optimal ELID and grinding parameters. Applications. Why ELID? So, you can see here lot of things are shown over here. Polishing is necessary to finish. UAG, ultrasonic assisted grinding, is being done over here. Then you have the single point diamond turning. This is the single point tool, diamond tool, and this turning process is taking place on this workpiece. And then you have the ELID, possible to use super abrasive wheels free from wheel loading and glazing. They are being used over here, and this is the wheel loading takes place. Then you have the deterministic micro grinding. Your wheel loading is overcome by removing the layers, that is the oxidized layers. So, high form accuracy and poor surface quality, high form accuracy and good surface quality. After ELID you get certain surface quality. So, with the help of MRF you can get high form accuracy and good surface quality. So, that is the advantage of combining ELID and MRF process. So, this is the common advantage of any hybrid process, because in a hybrid process you take the advantage of both two or more than two constituent processes. Nano surface finish on simple and complex shapes. You can see these are the different kind of the components, not possible with conventional processes at all to finish them, because here first thing they are complex in shape, as you can see many are there, they have free form surfaces and surface finish requirement is few nanometers. So, that is not feasible by conventional processes at all. Now, here you can see other components. New processes are necessary for finishing such kind of the optical components. Off axis parabolic mirrors you cannot finish by conventional processes, you have to go to ELID, MRF and other advanced finishing processes. Finishing of complex geometrical components like this as sphere, this can be finished by these processes only, not by conventional processes. You can see here a sphere over here, free form lens is there, free form I hope you understand, the surface which cannot be explained easily by mathematical equation. They are known as free form surfaces, and finishing and machining of these surfaces is very difficult. Only few limited processes are available which can do the job. Free form surfaces you can see here, and then example from day to day life. This is the lenses are used which are used in the specs. So, finishing of these components is very difficult, nice, but how to finish them, that is what we are saying. You can use the ELID and MRF process jointly. ELID research activities at University of Applied Sciences Dagenhardorf. Anyway, this is for one particular university. You can decide your own way how you want to conduct and what you want to conduct as research is concerned, but I will just tell you what they are doing. It is long back, it is very old slide for this purpose. Research areas for ELID grinding, fundamental research they are conducting on optimization of ELID process parameter. This is a common research activity where you try to optimize the any finishing or machining process parameter, where mechanism of grinding wheels, surface and subsurface analysis of finished samples or finished components. Now, precision finishing, hybrid ELID process development, that I have already mentioned to you, that ELID plus MRF, or you can combine ELID with other nano finishing processes are there. One of the nano finishing processes, there is another that is known as abrasive flow finishing or magnetorheological abrasive flow finishing, MRF process, which are developed at IIT Kanpur. There are many other processes which can be combined with ELID. Experimental investigations on ELID grinding. So, these are some of the areas on which research activities were going on in this particular university, but you can decide based on your available facilities and capabilities. Developments present and future. Future developments, control of the ELID process. This is very important, because once if you can control the parameters on the ELID process, then the finished component characteristics will be very good. An introduction to a knowledge based system, that is very much needed. So, you can use and expected results and possibilities. Once you have the knowledge based system, many things can be done automatically, and then the results will be better. Present and future developments that are taking place here in process monitoring and control of ELID process, optimization of the ELID and grinding parameter, building of a knowledge based database, and then a computer controlled knowledge based ELID system suitable for precision grinding. This is very important, because once you have the system development and you can control it with the help of computer, many inaccuracies causing factors can be eliminated or they can be controlled, and you get a better product. Development of knowledge based database for ELID grinding. You have the FHD, fundamental research, optimization, etc. This I have already told you, and based on this you can develop the empirical model and just have the knowledge database based on the experimental results from this. Knowledge based system reduces the requirement for operator. This is very important point, and then it becomes more database dependent system, and the probabilities of the human being error are minimized. No previous knowledge is required, user friendly and easy implementation. The system that you are going to develop should be definitely, I very strongly recommend that they should be user friendly, otherwise they will not be a successful system on the shop floor. And second point, they should be easily implementable, otherwise also if it is not so, then this may not get the popularity amongst the users, especially the industry users, and this will increase the robustness of the process. The future development, a knowledge based computer control system for ELID grinding is a must. Conclusions: chance by grinding, yes, and we have already discussed ELID MRF process chain. This we have already seen. Concluding remarks: from the experimental results and analysis, the following conclusions can be drawn. Surface analysis: the ground surfaces are also free from mid frequency errors. The ELID fine ground surfaces are with minor surface finish and low subsurface damage. The surface quality of the lenses produced by ELID fine grinding is suitable for finishing processes such as MRF. Form accuracy is another point with the help of which you can evaluate the process performance. The form accuracy depends on the stiffness and precision of the grinding machine. The excessive wear rate of the ELID grinding wheels during fine grinding, the optimal parameters have not been maintained throughout the ELID process, and if it is so, then you will not get the desirable results. ELID grinding process, because the process has not been controlled during the grinding process. Further concluding remark, ELID grinding is an efficient process for producing nano surface finish on various materials such as metals. This technique needs some expertise to produce the desired results. The robustness of the process can be increased using advances in control devices in software technology, and with further improvements in ELID technology, it will be useful to produce free form and complex surfaces. Thank you very much.